So now all the easy question of this playlist is done. All the easy questions are already been done in the previous video. So now I will start doing the mediums and start doing topic wise questions. So let's just start with the binary search pattern first, because it is the simplest pattern out there. So it will be nice if we start solving this first, as it will boost our confidence also in the algorithm approach. Okay, so let me just quickly erase all of this. Yes. So in this question, what we have asked is, there is an integer array nums sorted in ascending order. In every binary search algorithm, we will be given the sorted array. If it is not given the sorted array and the time complexity, they are satisfied with order of n log n time complexity, we can sort the array and then use the binary search algorithm. Here they are simply also asking to write an algorithm with order of log n time complexity, so we can't even do a linear search kind of thing. Let's see what the question is asking. There is an integer array nums sorted in ascending order with distinct values. Prior to being passed to your function, nums is possibly left rotated at an unknown index k. This k is not given to us. We need to find this k or somehow work around the given question and try to reach our answer in order of log n time complexity, such that the resulting array is, this is the definition of left rotated array, that somehow it is rotated to the left. For example, 0, 1, 2, 4, 5, 6 might be left rotated by 3 indices and become 4, 5, 6, 7. So the left rotated means this 0, 1 and 2 rotated to the left. Basically at first rotation, 0 go to the last place, this 1 shift to the left, then this 2 shifted to the left, then this 4 shifted to the left, and similarly then in the next rotation this 1 goes to the end. Now at the end it is something like 7, 0, 1. Then at last third rotation, our second number goes to the last and our array becomes this. So what we have to do is, given an array nums after rotation, we are also given a target, return the index of the target if it is in nums, or return -1 if it is not in nums. So for example, if in this example, let's say our target is 0, so we need to return the index of this, that is 0, 1, 2, 3, 4. This 0 is occurring at the fourth index, so we have to return 4 as our answer. For example, in this array, the target is given to us, that is 3, which is not present in this array, so we will return -1 here. So a brute force approach will be simply that we can do a linear search kind of thing, and whenever we find our our target, we will return the index of that. Basically it will be a simple answer. A single for loop will be running from 0 to the nth place, and whenever nums of I becomes equal to the target, we will return the ith index. Otherwise, at last, after the for loop, if none of the index is satisfying the property that nums of I is equal to the target, that means the target is not present in the array, so we will return -1, signifying that the target is not present in the array. But this will lead to the order of log n time this algorithm, that brute force which I just told you, will result in the order of n time complexity, basically linear time complexity, because we will be running our for loop from 0th to nth. This is not what the question is asking, so we need to do some kind of binary search algorithm in this question. So let's just quickly copy our input. I hope the brute force is quite simple and it is clear to you guys, so I don't need to explain that again and again. I am just copying this array 4 6 4 5 6 7 0 1 comma 2. Okay, so this is our array. Yeah, so we need to do something that is order of log n time complexity. So how we can approach this question? It is quite easy to do a brute force approach. We will just search in this array using a for loop. For I is equal to 0 to nth, we will do a for loop and we will compare each. Is this equal to the target? Is this equal to the target? Whenever our target satisfied that property, we will return that index. But this is not, again, this is not asked in the question. So in this question, let's say our target is 6. We need to return 6 as our, we need to return the index of the 6th element in the array. At what index this 6 is coming? For this, the answer will be 2th index, because at 0 1 2, at 2th index our 6 is appearing. So we need to return the answer to be equal to 2 using binary search algorithm, because we need a order of log and time complexity algorithm. Okay, so let me just quickly do this. These are the indexes of the array, and our size of this array is 7. Okay, so you know one thing, that in order to apply a binary search algorithm, what we needed, what are all the parameters that are required in every binary search algorithm? Firstly, a sorted array that is sorted, a starting index, ending index, and our target that which we are finding. We only need these things in order to do that. In this question, we can define the starting index, we can define the ending index, we are given with the target, but the only catch here is that we don't have the array which is sorted. This array is not sorted at all. You can clearly see that this array is not sorted, because after 6 there is 7, and then after 7 the 0 is occurring, which is lesser than the 7. So this array is not sorted at all. But here is one keen observation that you can make in this question, is that this part is sorted array and this second part is also a sorted array. So the left is a sorted array and the right is also a sorted array. What we can do is we can independently apply binary search to these two arrays independently. Basically, first we will do binary search in the left part, and then if we don't find our target in the left part, then it is guaranteed that it is there in the right part, or it is not there in the array itself. So we will do a binary search on left part also. If say in the left part our answer returned, here in this case this 6 is present in the left part only, so when we do binary search on the left side, it will return 2 and we will return this 2 as our answer. But let's say if our target was 2, then this binary search of the left side will return -1. So we will search on the right side. This is the left side and this is the right side. If we find our answer on the left, we will return that index. If we don't find our answer on the left, we will do search that on the right side of the array, and if we find that there, then we will return that index, otherwise we will return -1, signifying that the target element which we are looking is not present in the left subarray also and the right subarray also, which both of the subarrays are sorted in this case now. Okay, so I hope this is clear to you guys now, that whenever there is a sorted array given to us, and let's say in whatever order we rotate it with the kth left thing, it will be something like, let's say our k is 1 in this case, so we are rotating it once, so it will become like 2, 3, 4, 5, 6 and 1. Here also the left part is sorted, and right part is sorted, so we can do a binary search here also and here also. Okay, now let's say our k is equal to 2, then it will be something like 3, 4, 5, 6, 1, 2. In this case also our left is sorted and right array is also sorted, so we can apply binary search algorithm here. And it is not the case, we can apply binary search in constant times. For example, it is not an issue that we implement a binary search one time only. No, we can also apply in it 2 times, because let's say if we apply binary search 2 times, which is the case in this question, then our time complexity will be something like order of log n plus order of log n, which will result in order of 2 log n, and the time complexity will remain order of log n only. So this is not the issue. Here we can run our binary search in whatever ways we can do, like in how many ways we can again and again do binary search, that is not a problem. But this constant thing should not be equal to n. In that case it becomes n log n, that is the worst time complexity than this log n, or even linear time complexity, that is worse than that also. So we need to take care of that also. So we only need to apply binary search in 2 times, in constant times, in order to get our answer. As long as we are doing that, we are in the boundaries of the answer that question is accepting. Okay, so now it is clear that in order to solve this question, we need to apply binary search algorithm 2 times, one time on the left side and the second time on the right side, to find that target. But how to have a boundary here, how to find this index? Basically we need to give starting index, ending index, starting index and ending index. How to find these indexes of this? Basically our job will be over if we find this part, basically this ending part or this starting part. If we found these, then we are over. So how we can find this? Using a binary search algorithm. Okay, so let's just quickly write a binary search algorithm first, because our classic binary search algorithm is being used 2 times here, one on the left side and the other on the right side. Then we can somehow figure the start, end and middle element during some other time. So let's just quickly write the algorithm first. For the binary search algorithm, it is somewhat like public int, let's call our function name binary search. It will take the array, the sorted array. It will take the sorted array. So we need to take care that we need to pass the sorted array here. We can't just directly pass our nums and accept an answer from this binary search, because the nums is not sorted. Either we first need to sort that, but if we sort that, then you know the best optimal time complexity sorting algorithm is n log n. That will fail in this case, so we can't use that here. So, and in our binary search, as you know, we need to define the boundary, because in the sorted array also it will be something like divide divide divide, so we need, it will break our bigger array into the smaller sub areas, sub arrays, so it will need some boundaries. So it will take starting index and ending index, and of course it will take target, that which we are trying to find. And the base case for this binary search is always that if start becomes somehow greater than end, which can never be the case in a binary search, that how the start becomes greater than the end, because the start must be at the left side of the array and the end must be at the right side of the array. But somehow if by dividing and dividing, when the start and end are closing to each other and somehow they crosses each other, then we are done, that we have to return our answer. In this case we will return -1 in this case, because if this condition is reaching, that means the sorted array is being searched by binary search, but we don't find any target itself, and the start is closest to the end, so we will return -1. Now we will calculate mid. Now I have already explained you why we are calculating mid like this way, because if we do something like end plus start by 2, then end plus start can lead to integer overflow and will break in some edge cases. So we do some workarounds and some trickery of maths and define mid like this. Now if our target is less than ARR of mid, if our target is equal ARR of mid, we have found our answer, so we will return mid. And if target is less than ARR of mid, basically in this case the target is at the left side, and we are at the right side, because ARR of mid is greater than our target. So we need to search on the left side of the array, left part we need to search. So we will do end is equal to mid -1. Else we will do start is equal to mid +1. This is basically a simple binary search algorithm that we are performing here. There is nothing special in that. Okay. And now we will recursively call and reduce the boundaries of this. We will call and return binary search on the starting array only, sorted array. Our start in this case will remain same, but our end will change to mid -1, as I said you earlier, and our target will remain the same. So we don't need this statement, because we are already passing mid -1 to our end, so there is no need to do that. Similarly here also we don't need to specify our start, just change our start here only, that it is mid +1 and this is our end. Okay, Now our binary search algorithm is completed. Let's just see if there are any issues in this. So let's just return 0 for now for debugging purposes. Yeah. So this is sorted array. This is sorted array. Yeah. So now the binary search algorithm is quite working. So let me just check once that is binary search internal calculations are also correct or not. Binary search on whole nums, and our starting will be 0 and our ending will be nums dot length minus 1, basically our whole array, and our target will be same target only. Let's just run this. Okay, so this is running somehow, but as we know that we need to like define a left sub array and the right sub array in order to pass this, what I was looking was is to add a test case here uh, where the array is sorted array only to check is our binary search algorithm is even correct or not. Let's say we are trying to find 5, so it should return 0 1 2 3 4. It should return 4 as the answer. So let's just see what it is returning. Okay, so for this case, when our target is 5, the output is 4 and the expected is 4. So our binary search code is correct. So we can reuse this for the left part and the right part as I was talking to you. So this is fine. Our binary search algorithm is done. So let me just quickly just revise what till now we know and what till now we have written the code for. So as I have told you that in order to solve this question, we need to call binary search on the left sorted array and the right sorted array. So we have defined this binary search where it is taking a sorted array, starting index, ending index, and the target. Now we need to somehow break our original nums array into these two left and right sorted subarray, and that must also be done in order of log n time complexity, because we can't go order of n time complexity because that will break our question's expectations. So how we can find this index? Basically what I am saying is, let's say our array is something like this. uh, we have make a blueprint that is binary search algorithm. We can use this whenever we want. We will reuse this again and again in the next questions also, so that's why I give so much time into this question. So we need to find pivot index this pivot index so that we can search in left subarray and right subarray, as I have told you earlier that we need to break this array into two sorted subarrays, one on the left, one on the right. To do that, we need to find this pivot index, and what are the properties this pivot index is satisfying. Let's see this, that this pivot index will surely be greater than its left. Basically this ARR of pivot index will be greater than its previous, and this pivot index will also be greater than the one element which is ahead of it, which is p underscore I plus 1. So basically this is the greatest element in the array. This will also be satisfied by this pivot index. So these two are the properties of this pivot index because of this left sorted subarray, that the left element to it is also smaller than this and the right element to it is also smaller than this. No other element or no other index will satisfy this property. You can see this 4 does not have any left part, but it is smaller than the right part. Similarly, the 6, it is greater than the 4, but it is lesser than the 7. Similarly, this 2, it is lesser than 3 but greater than 1. But only 8 is greater than 7 and greater than 1 also. It is greater than its left element and its right element. So this is the only element that satisfies this property. So we get our if statement, that we need to do a binary search kind of algorithm here also, because we needed a logarithmic of n time complexity code. So we will calculate our mid again, but now if let's say our ARR of mid is greater than ARR of mid minus 1, and our ARR of mid is also greater than ARR of mid plus 1, then we reached our pivot index. Basically we have to return this pivot index. Then our pivot index will be p underscore I will be equal to mid. We got our pivot index in this condition. This is the only condition that will be satisfied by the pivot index only. Now what will be in else part? Let's say else if let's say if our middle reaches here, then by this property we will get our pivot index. But what if in our mid calculation we somehow land somewhere here? Now one thing is clear, that this if condition will fail for this calculation. Let's say if mid comes out to be 0 1 2, let's say if mid come out to be 2, then in this case this if condition will not run, because let's say if in our our ARR of mid is not greater than ARR of mid plus 1. So now it is quite clear to you guys that if somehow the mid is here, then it is quite clear that let's maintain a start pointer here. We will compare our ARR of start and ARR of mid. Now let's say ARR of start is 4, ARR of mid is 7. Clearly 4 is smaller than 7, so we will find our pivot index surely in the right side. So in that case we will do S is equal to mid plus 1, because we will find our required pivot index on the right side when this condition is satisfied, that ARR of start is greater than ARR of mid. So this is one else if condition, that if our ARR of mid is greater than our ARR of start, then in this condition we will search in the right side of the array. And in order to go to the right side, we have to shift this star to the right. So we will do S is equal to mid plus 1. And now the last else condition, that will be automatically will be something like that: a ARR of start is lesser than ARR of mid. Now in this case the opposite will happen, so we will update our end to mid minus 1. Basically in this case, let me just copy this quickly. 4 6 7 8 1 2 3, 4 6 7 8 1 2 3. Now let's say our start is at here, our end is at here, but somehow our mid calculation is at here. I know this is not the case here, but we are supposing one specific iteration that can occur internally when we divide and we calculate again and again this mid and start and end indexes. So this can be the case that somehow we end up here, that this condition will be satisfied, that ARR of S is greater than basically ARR of start is greater than ARR of mid. See here, ARR of start is 4 and mid is 2, so clearly ARR of start is greater than ARR of mid. So this condition will satisfy. And now automatically think in the sense of array, that if we are here, if the middle is at here, if the middle is at 2 and our start is satisfying this property, then and we need to find this pivot index, we need to reach somehow here, we need to do something like middle reaches pivot element, we need to go here. So clearly if we are here, then to reach the pivot index we need to go left side, in order to do that, what we can do is we will shift our end to the left side, so that in the next iteration when we calculate our middle element, due to this end being mid minus 1, as it got decreased, it will go to the left side. Our middle element will go to the left side due to the smalling the value of the end which we are calculating. By doing this, at last we will find our pivot index by doing this. And once we find our pivot index, and once, let's say if we found our pivot index, let's say in this case it will be 0 1 2 3, it will be 3. So what will be our two sorted subarrays in that condition? It will be starting from 0 to our end will be and 1 will be, basically this is start 1, basically this is the left subarray I am talking about, basically this left sub array I am talking about. So it will be something like starting from start, which is equal to 0 to pivot index. So it will be starting will be at the 0, but the end 1 will be at the pivot index. Now the right side will be the right side will start from here, that is pivot index plus 1 to our end. So it will be, now the S2, the starting index for the second sorted right side array will be pivot index plus 1, and ending index will be at the length of the subarray minus 1, n minus 1 basically. We will do independent binary search here, and we will search in this side. It will be order of log n time complexity only. This is also a binary search kind of finding, so this will also be log of nth time complexity. Again, we are doing binary search kind of algorithm 3 times, so it will be log n plus log n plus log n, which will be order of 3 log n, and we can drop the constant from the time complexity calculation, so it will be order of log n time complexity at last, and we will get our answer that if the target is in the left subarray, we will return the middle element. Otherwise this left binary search will return -1. If this return -1, we will search on the right side. If the right side returns some element, middle element, or the calculation, the target which we are trying to find the index, then we will return that index. Otherwise this will also return -1. So if both of these, right search and the left search, returns -1, we will at last finally return -1, signifying that we don't find the target in the whole array. In the left sorted array also, in the right sorted array also, we don't find that element which we are looking, so we will return -1. Now let's just quickly write the code for this. Basically I have written all the algorithm here only, so there is just, I will do this quickly. Okay, so let's just quickly calculate the length of the nums array. Let's make our start, that will be at the 0th, our end, that will be at n-1. We will do a while loop search. Also we need to store pivot index somewhere, so we will write a variable p_i. At last we will store the pivot index here, as I have shown you in the tablet. So now while start is less than end, this is a standard binary search condition that we will run the while loop until our start is at the left side of the end. If they somehow crosses each other, we will stop there. Now the condition of the first if condition was let's just quickly calculate the middle element first, that int mid is equal to start plus end minus start by 2. The first condition was simple, that if ARR of mid is greater than ARR of mid -1 and ARR of mid is greater than ARR of mid +1, that if ARR of mid is greater than, sorry, this is not ARR, this is nums, so this is nums. If ARR of mid is greater than ARR nums of mid -1 and nums of mid is somehow also greater than nums of mid +1, then we have found our pivot index. So we will just update our variable. So in this case we have found our pivot index. Else if condition was when we were searching in the left side and in the right side. These two were the different conditions. Else if condition, that if ARR of mid is greater than ARR of start, basically ARR of middle is greater than ARR of start, then we will find our pivot index in the right side. If we will find that in the right side, so we need to shift middle element to the right side, and in order to do that, in the calculation of start plus end by 2, our end is fixed, so we have to like shift start to the right side. So we will shift our start from 0 to middle +1 in order to reach the appropriate right side, in order to find pivot index. So now else if nums of start is lesser than nums of mid, we will go to the right side, that is s is equal to mid +1, and in the last case, else case, we will go to the left side, so we will do end is equal to mid -1. If you like somehow unable to get like either to update end here or to do mid +1 or mid -1 or or here to write start is equal to mid minus 1 or end is equal to mid plus 1, then I will suggest you that you write the template of this first and then like do trial and errors. You can do first middle plus 1 and run the code and check is it working. If it fails, you can interchange these two conditions. If that also fail, then you have to do a dry run. Basically, this will save the time and thinking in depth of these condition in OAs. Okay, now if after this while loop our pivot index should be there, so let's just quickly check is in our calculation our pivot index is getting calculated correctly or not. So what we will do is we will at last return this pivot index and we will check in these examples that for this, let's say our pivot index is at 7, which is 0 1 2 3. So this while loop, this pivot index should have this 3 in it. So let's just run this once. Okay, there is some error occurring. If else if. Okay, there is one thing I need to tell you, that here we are calculating mid minus 1 and mid plus 1. So here one thing can occur is that, let's just do this first maybe. Maybe this is reversed, so let's just do this. Some kind of TLE is occurring. Let's do one thing, that this is the else if condition and let's just make this also a else if condition only. Else if our nums of s is less than nums of mid, we will do end is equal to mid minus 1. Okay, and here what we are doing is if nums of mid is greater than the left and if the nums of mid is greater than its right also, then this is the pivot index and we will break our loop. Okay, so here one break will occur because we are done. Here we have calculated our pivot index, so this is there and this was correct. I believe I fumbled that. So if ARR of mid is greater than ARR of S, if ARR of mid is greater than ARR of S, we will go to the right side. So yeah, this is correct now. Yeah, so now see our output is getting correct because this was the pivot index, this 7 was the pivot index and we are getting output as 3 only, which is 0 1 2 3 and at the 3th place we have 7, so this is correct. Here we are getting this 3 as a pivot index, 0 1 2 3, and this is also correct, so no worries in that. Yeah, so our code is working right now. Now we have to do a left search and the right search, basically this. Now we will do a left search and a right search. Let's just do a right search, that if our binary search on left side and our binary search operator is taking a sorted array which will be our nums only. Starting index for the left part, as we discussed, the start will be at the 0th index and the ending will be at the pivot index. See, for the left part, our start one will be at the 0th index and our ending will be at the pivot index. For the left part, our start will be at the 0 and our ending will be at the pivot index. And we will pass the target which we are looking for. Now, if this does not return -1, we can simply return this again. We can simply return this, signifying we have got our answer in here only, in the left part only. Basically we are doing 2 times this binary search, so we can improve this algorithm. So let me just do this, that int left is saying that this is our answer. If the element is in the left side, it will return the index of that, otherwise it will return -1. And our right is saying that the answer is in the right side. For the right side, as I have stated, that the start of the right will be pivot index +1, so it will be pivot index +1 till our end is basically n-1 target. Now we will return math.max of L_s, R_s. So what exactly is this statement? This is basically a stylish way to write this, that let's say if our answer is at L_s at the left side, we will store our answer in the L_s part. It will look something like 3, 4, 5. It will not be something like -1. So then our right side will automatically return -1. So when we do math.max of these two, this -1 will not get listened and our answer will be at L_s. Similarly, in the vice versa case, let's say our element that is we are searching for is present in the right side, so this L_s will return -1 and this R_s will have something, let's say 0, 1, 2, 3 or some kind of index which is a positive index. Then if we do math.max of this, then our R_s will be listened and L_s will be dropped because it will be -1. And if our element which we are searching is not in the left side and also not on the right side, then these both will have -1 in them. Then the math.max of -1, -1 will be -1 only. So I hope this is correct. Okay, so I was expecting this error because of this condition here only, because here we are calculating mid -1 and mid +1. What can occur here is that, let's suppose our middle somehow is 0. Then if we do middle -1, it will be index -1 out of bounds, because our length can never go to the negative side. And let's say if somehow our middle is at end only, the nth position only, then if we calculate, if we will try to find mid +1, then also it will be out of bound error, because let's say our length of array is say 3 and we are trying to get the element that is at the 4th length, which is not possible in Java at least. So before finding this mid -1 and mid +1, we need to just make sure once that mid -1 is calculatable, is gettable. Our nums of mid -1 is there. Basically mid -1 is greater than equal to 0. It is not going in the negative side, because if it goes to the negative side, then there is no point in getting the nums of -1. as in Java it will return an error that our mid minus 1 should be greater than equal to 0 and our mid plus 1 should be less than our n, the length of the array. Let me just define like this. Maybe there is some error again occurring. So why this error is occurring? Maybe you can try different things to encounter this. You can try to do this like add equal to sign here and run this and check is this working or not, because these are the only edge cases where this binary search algorithm fail. Okay, so this is worsening our case, so this is not the right thing. You can also try to reverse these also, but I don't think this is the case here. Okay, so if our start is less than, we are searching to the this side. If our start is greater than nums of mid, we are searching on the left side. Okay, so what will happen if our start is equal to our mid? If that is the case, let's just try to handle that by adding equality sign here. Okay, but our answer got improved. Basically, earlier it was failing 5 out of 196, but now every test cases have been passed. There is still one thing that is occurring. Maybe this thing is there only, that our start should be less than equal to our end, because in binary search algorithm this is the case. This is the general case. Let's just try to do that. Okay, so now this is getting accepted. So I hope you get an idea that in binary search algorithms, these are some different combinations of edge cases that you can try in order to pass these test cases, because the answer somehow is the combination of these different combinations of the start and these if else conditions, or somehow the answer in some question is s less than end, but in some it is s less than equal to end. So these are the only thing you need to take care in these binary search kind of questions. Now let's just quickly try to solve this question also. Let's just remove all the thing from here. So now this question is stating that find first and last position of element in sorted array. So this time we have given the sorted array, so we don't need to like have a pivot index or like sort it or some kind of thing. Also these guys are saying that algorithm must be in order of log and time complexity. That is the standard in binary search algorithm. Whenever the interview says that provide an algorithm in order of log and the array is already sorted, then you know binary search is the go-to algorithm. Given an array of integer nums sorted, find the starting and ending position of the given target value. If the target is not found in any array, return -1 -1. you must write an algorithm with order of log n time complexity. Okay, so let's say here our target is 8, which is at this position and this position. So we need to find the left side, leftmost 8 that is occurring, and the rightmost 8 that is occurring. The leftmost 8 is occurring at 0 1 2 3 third index, so we are outputting here third. But the rightmost is occurring at the fourth place, so we are outputting 0 1 2 3 4 4. So we are outputting 4 here. If the element is not there in the array itself, we are returning -1 comma -1. So that is standard. So our answer will be a array that is of length 2. So let's just quickly write that. Our answer will be a 2 length array, which will store the leftmost index of the target and the rightmost index of the target in the array which is occurring. Okay. Let's just also store the length of the array itself. Let's just call this nums array because I somehow is more familiar with the array and I always use ARR. So let's just do that. Length. Okay, now n is also sorted. We have to do a binary search algorithm also. So I am thinking to let's copy our binary search. Yeah, why not? Let's just copy our binary search algorithm that we wrote in previous question. This is the standard binary search algorithm that I am copying, not the algorithm of the main question that was the previously asked. So this is a simple binary search algorithm that I am copying, because there is no point in again and again writing the same lines of code. Okay, and at last we have to return our answer. So let's just return ANS. So this template, this is some kind of a template which I have built. Now the main logic or the main code will occur here. Now let's just quickly write the main algorithm also for this code. The array is 5 7 7 8 8 10. Array is 5 7 7 8 8 10. For the first time, let's make the boxes also. So this is the sorted array which we have been given, and also it is given that our target is 8. So what we have to return is the leftmost part and the rightmost part. If this was asked in a brute force kind of setting, or you quickly need this kind of thing, you can do a order of n linear search, linear kind of thing, where you can run a for loop and get the answer very quickly. But this is a binary search setting, so we need to do some workaround here. We have our binary search template, binary search main algorithm template also with us, which takes an array, sorted array, a starting index and ending index, and a target to search. So now we have to do some kind of thing so that we get our leftmost target and the rightmost target which we are looking. Here it is 3 and here it is 4. And we need to like submit that answer in our some kind of a 2D array, where at last we will return the answer here. The index is here, this is the left index and this is the right index, and if the element is not present in the array itself, we will just return -1 comma -1. And it is also clear, let's say in this question, let's say our target was not 8, let's say our target was 5, then our answer will be this. Basically our left is also 5 and our right is also 5, so we will just return 0 comma 0 here where the 5 element is occurring, because there is no two elements where there can be a left or a right, so we will just return 0 comma 0. In this case, if the target was 5, basically a single element in the array, if we are searching that. For 10 also it will be the same, but in that case it will be 5 comma 5 because it is occurring at the fifth index. Yeah, so this is quite easy to understand and this is not something quite complex, right? Okay, so let me just quickly give you an intuition that how to approach this question. We have to find a left and a right. So let's just make a example of our own so that we can get a better understanding of this question. Let's say we have given a sorted array. 1 2. Now let's say our 3 is occurring this much time, and then there is 4 and then there is 5. Now can you tell me what will be the answer in this case? In this case our answer will be something like, the let's say our target is 3. We are searching for 3's leftmost and rightmost. 3's leftmost is here and the rightmost is here. So this will be our left, this will be our right, and clearly it is 0 1 2 3. So this is 2 and this is 0 1 2 3 4 5. This will be 5. So we need to return 2 comma 5 if this was the question, if this was the array given and the target was 3. Now how to apply binary search here? What we can do is, we can do something actually very smart here. It is given that all the element that is occurring here will definitely be a integer. So if the target is 3, then it is clear that to the left of this, will either be a 3 or some element that is smaller than 3. It can be 1, it can be 2, it can be any number. Let's say it is 2. It can never be the case that before 3, in the left side of the 3, there is some pointed number, let's say 2.5. This can never be the case in the array. This can never be the case. And similarly to the right side of this 3, there can either be a 1 more 3 or a 1 more 3 or a 1 more 3 or a 4 or a 5 or a greater element, but there can never be a element that is between 3 and 4, that is, let's say, a pointed number, let's say 3.5. This can never occur. But you can clearly see that this 2.5 is less than 3 and this 3.5 is greater than 3. So what we will do is, we will define a target, our left target as 2.5, and we will define our right target as 3.5. Basically this is nothing but our original target minus 0.5, our original target plus 0.5. So we can like calculate this if we have our target which is given in the question. So now what will happen if we try to run a binary search here when our target is 2.5? Let's say when our target is 2.5, then our binary search is looking for something that is not present in the array, that we know but the algorithm don't know. So it will try to search 2.5 in this array. What it will do is, it will initialize it with start, end, middle, and it will try to find this 2.5 which is less than 3. So in the left side, so we will reduce our end to mid minus 1, so it will go to here, then our start plus mid minus 1 will somehow reach here too. So by doing this and this again and again, you can think of it that it will somehow reaches here when our start is at here, our end will be at here, and it will calculate our middle element also, which will turns out to be mm 0 plus 1 by 2, which will turns out to be 0. And here when we do this again, we will run if we will calculate our middle element, that will be 2, which is smaller than our target. Our left target is 2.5, which we are searching. So it will say our target is somehow in the right side of the 2, but our target is somehow in the left side of the end. So there will be some kind of narrowing down of these start and end. And when this start and end will fail, will when our end reaches before our start, something like this, when our end reaches here and our start reaches here, and at last we will just return our start as our leftmost point which we are trying to find. Similarly for the right side also, when our when our right side target is 3.5, the same setting will occur. The binary search will narrow down the array again and again while updating starting pointer, ending pointer and middle pointer, and it will reach a case something like this. It will reach the case something like this. Let me just clear some space for this. For the left part we are searching for 3.5. We are searching for 3.5. So it will reach something like here. When we here the starting pointer is at 0, 1, 2, 3, 4, 5. 5 and end is at 6. When we do try to find the middle element, it will be at 5th index again, so it will be here. So now also you can see that when we do binary search here, it will say that our target is in the right side of the start, because we are trying to search 3.5. So it will update our pointer, and our pointer will update it like something like this, that our start will go here and end will go here, and at last we will simply return this end because this is the rightmost 3 which we are looking. In same fashion we will get the S here for the leftmost part, and here end as the rightmost 3 which we are trying to look. I will write the code for this, and I will try to explain this side by side to you also, that how we are trying to do this and why our answer is coming out by doing this, and how this 3.5 search occurred. You can think of this like something like this, that let me just rub all of these explanation. So you can think of this something like this, that let's say if we are trying to search 2.5 which is not present in the array itself, our binary search will somehow point to this thing. Basically it will return -1, but we will modify our binary search algorithm in such a fashion that you know that for this our start will be at here, end will be at here, and our middle calculation will also be at here. And if we see our if condition for the binary search, what are the if condition for the binary search? It is such that if our target is greater than ARR of mid, which is the case here, that our ARR of mid is 2 but we are searching 2.5, so target is greater than ARR of mid, so we need to search in the right side. In order to search in the right side, what we do, we update our start to middle plus 1. If we do this, what will be our start? It will be 0 1 1 plus 1, that is 2. Our start will go to here, and at last we will return our start, and this is the answer which we are trying to look for this case, our 2. Similarly, for the right side also, we are trying to search target plus 0.5, that is equal to 3.5, and our binary search will narrow down by using this start pointer, end pointer, and so on, and somehow reaches here. It will point that our answer that we are trying to look is here, between this 3 and 4. Basically our start will be at here, end will be at here, and the middle will be at here. Now for this case, it is clear that if we try to see our if loop for this condition, that our target is greater than mid plus 1 here also. Okay, here also it is something like that, the target which we are trying to search is still greater than ARR of middle. Here also we will do start is equal to mid plus 1, 0 1 2 3 4 5 6 5 6. So then our start will go to the 6, and in this case our start and end and all will be at 6, so our middle will also be at 6. But now it will try to say that our middle is 6, so let's just calculate ARR of mid. ARR of mid will be 4 in this case, which is greater than our target which we are trying to find, that is 3.5. so our in this case our end will update to mid minus 1, so our end will be 6 minus 1, that will be 5. When our end reaches here, our while loop will break, because start is greater than equal to end will be the case in this case. So we will return this 5 as our answer, and this 5 is stored in end, because when this while loop break is that when our end somehow goes to the left of start, and this is the case where this is breaking, so we will return end in this case, the left side, and in the left part we will return start, because here our start will go to the right and we need this start at the starting point. Let me just quickly write the code for this so that you can get better understanding of this. By writing the algorithm on the tablet, I realized that we don't need our standard binary search, because we will need to define our floating point to handle the decimals that we are trying to search in the target. Also, at last we will not return -1 here, but we will return start for one and the ending element for the other. Okay, we can work around here, so let me just keep it as it is. But now our target will not be an integer, but it will be a float data type. As I have discussed that in order to do that, we need a float data type. We will do target minus 0.5 or target plus 0.5. Basically, any point decimal between them works. You can also do minus 0.1, minus 0.2, minus 0.9. Everyone will work, because in all the cases, let's say if we do t minus 0.1, then 2.9 will be always lesser than 3 but greater than 2. So that also will work. Any point number between 2 and 3 will work. Basically every decimal number between target minus 1 and target will work, and every float number between target and target plus 1 will work. Let's just define our float data type. For the left target, that will be target minus 0.5 f, and our right will be plus 0.5, target plus 0.5. Let's just quickly run this and see is our syntax correct for the floating point, because most of the cases we don't use them. So yeah, the floating point syntax is correct because there is no runtime error, no syntax error basically. Okay, now do we need to find this left and we need to find this right. In order to find this, we will need to run our binary search algorithm two times, one for the left finding when our target will be 2.5, and one for the right side when our target will be 3.5, basically target plus 0.5 and target minus 0.5. So we need to run our binary search algorithm two times. So let's just do for the left part first, that our left answer is binary search of sorted array, comma, what it takes, a starting index, ending index, and a target. Our starting index will be 0, our ending index will be n minus 1, and our target in this case is L underscore T. And we have changed this to a float, so there is no issue there. And our right, what will be our right? Our right will be same as these parameter, but our target will change. Our target will now be target plus 0.5, this one, target plus 0.5. And now we will store this L and R in our binary search, in our answer, sorry. Answer of 0 will be L, and answer of 1 will be R. Let's just run this and see is this working or not. Okay, so this will not run because here we are returning minus 1, but I have told you that for the left one we will return we have to return start, and for the right one we have to return end. So we need to modify this return statement here. Okay, so yeah, so we need to define two of these function, basically three of these functions. So let's just define three of these function. This is our binary search classic, this one will be the binary search for the left, and this will be the binary search for the right side. And in our classic one we don't need float, integer will work, because we will just check is our target even present in our array or not. So let's just do one thing, that if binary search of, let's just initialize our answer with -1, -1, that if our binary search classic is saying that there is no target element in the array itself, then we will simply return answer, basically -1 comma -1. We will return -1 comma -1 when the target is not present in the array. Say, see, in this case also the target is 6, which is not present in the array, so we are returning -1 comma -1. So I have initialized array with -1 comma -1, and if our binary search classic, basically simple binary search algorithm, is saying that our target, that is 6, is not present, we will return -1. So in this case the -1 is getting returning, so it will return -1 comma -1. Now for the left part we need binary search left, and for the right part we need binary search right. And what will be the changes in the function is that, as I have told you, that for the left part we need to return starting index start. We need to return this s. So for the left part we will not return -1, we will return start, and for the right side we have to return end, and for the right part we have to return end, because end will have our solution for the right side of this. So in our binary search right algorithm we will not return -1, but we will return our end pointer. So now this code should work. Let me just run this and check. Okay, so we need to like internally modify this also. This is our classic, and this is our left one, and this is our right binary search algo. Okay, few test cases are passing. Let's hope all the test cases are passing. As you can see, all the test cases are passing and our solution gets submitted, and this is a order of log n time complexity solution only, so we can't go more better than this. Okay, now it beats 100%. I don't know what was the issue earlier. Basically our solution is optimal. This is the best solution you can get. So now just quickly try to solve these two questions also, then our binary search medium questions will be completed. Let's just quickly erase the code. So for this question you are given an m cross n integer matrix with the following properties. Each row is sorted and the first integer of each row is greater than the last integer of the previous row. Given an integer target, return true if target is in the matrix or false otherwise. And we must write an algorithm that is in order of log m cross n time complexity. So one key observation here is that every row of this matrix is sorted. As we know, we have to apply our binary search algorithm, so we need the sorted rows anyway. So see, the row 0th is sorted, row 1 is sorted, and row 3rd is sorted. Similarly, all the columns are also sorted because of this property. The integer of the each row is greater than the last integer of the previous row. So integer of the first integer of the row, this 10, will always be greater than the last integer of the previous row. Due to this property and due to every row is sorted, we have something like every row is sorted and every column is also sorted. And our numbers will be in inclusive range of this in some row. It can never be the case that our 3 is occurring here also, and let's say our array is 1 3 5 7 here, and here our row is 1 2 3 7. So this can also not be the case because of this property that previous row element last row will be smaller than our the next row's first element. Now, how to solve this question? You can think of this as we have to apply a binary search on a row, but in order to reach exact row, the appropriate row which we needed, we can also apply our binary search on rows also, basically column wise, to reach the row, the appropriate row. What I mean by that is, think of this as a matrix. Of course, we need to, like, let's say we somehow reaches the correct row, then we just need to apply a binary search and we will get our answer. But to reach a row, a correct row, what we can do is think of this 1 10 23 as an array. We can apply a binary search in 1 10 and 23 and find our 3. So what our binary search will say is that it lies somewhere between 1 and 10, and we will return our end here in order to get this 0th row. Either the end will be the answer or the start will be the answer. We can do trial and error for that also. So what I mean by that is, let's just quickly try to explain the logic here. Let's say this is our array 10 23. 11 16 20, or here there can be any number. Let's say this is how the array is. Say somehow we reach this row. Let's suppose there is some blue box which is returning our answer, the correct row which we needed to find our target. Here the target is 3. So if we somehow got this row, we can apply a binary search here to get this 3 in log of n time complexity. That is not a difficult part. But how to build this black box which will return an appropriate row using binary search? That is the tricky part. Now let's just try to find that also, that how to do that. Let's say our target is 3 only. Now think this as a row. Let's say we have a row that is 1 10 and 23. Our target is 3. So when we do a binary search here, start will be at 0, end will be at the last, that is 2 here. When we try to do binary search here, middle will be calculated, that will be 1. So what will be the ARR of mid? It is 10, which is greater than our target. So we need to search in the left side. In order to search in the left side, we will shift our end, we will update our end to mid -1. So our end will become mid -1. Our end will become mid -1. In that case, our end will become 1 -1, that is your 0th case, 0. And if our end becomes 0 and our s is 0, end is 0, s is 0, so our middle will also be 0 in the next iteration. And what is the ARR of 0? That is 1 in this case, and this 1 is greater than our target. So now our middle element is pointing here, and it is saying that the target which we are searching is in the right side of the middle. So what we will do in that case, what we do is we update our start So how to update our start? We do middle plus 1, and middle was 0, so 0 plus 1, so our start will go to the 1 and our end will go to 0. And our now in this case, when this calculation occurs, our while loop will break because our start will become greater than our end. Basically our start and end should be like this on the left side of the end, but when this case happens, something like this occurs, that our end somehow reaches to the back of the start. In this case we stop our recursion or while loop, whatever we are approach using. Now see the position of the start index and the end index. Starting index is pointing to the next element and ending is pointing to the previous one. And now let's just see what in this array our start and ending index at last will be. At last our starting index will be pointing at here and our end index will be pointing at here. You can clearly see to get this 1th row we need end. We don't need start, we need end. So what we will do is we will call something like ARR of end, then this ARR of end in the matrix will return this row. Basically we somehow reach this row, because this, what will this row be? This row will be ARR of end. I hope I have tried sufficient to explain you. I have also dry run it and explain how end is coming in the back of the start and why we are using end here and not start pointer here, because start pointer is pointing at this this array and we don't need this, we need this to find our target. I hope you get this now clearly. So let's just quickly write the code of this. I have already done and wrote binary search code multiple times, so I don't think that will cause any issue. So let's just quickly do this. Our m cross n is the size of the matrix, so let's just define that. Int m is equal to matrix dot length. Our n is matrix of 0 dot length. Now we need to define our start and end index. Int start will be at 0, our int end will be at. Now see what will be our end. At first we will try to find the appropriate row first, so we will do binary search here. We will do binary search like this. So our starting will be at 0 but our ending will be at basically m minus 1 or the length minus 1. Here will be our end at start, because first we do binary search on y-axis, then we do it on x-axis, because we need to find the correct row in order to do that. We can also do the otherwise, but I have explained you like this, so let's just stick to this only. M minus 1. Now let's just initialize our while loop. In binary search, while loop condition revolves between s less than end or s less than equal to end. So here it is s less than equal to end, because in the dry run I have shown that when s is equal to 0, e is equal to 0 and m is equal to 0, we were calculating the binary search, so we were calculating the middle element, so we need that also here. So the condition here will be s less than equal to end. Let's do our middle calculation. It will be start plus end minus start by 2 again. Now this is the case, let's say the element which we are trying to find, the target element which we are trying to find, somehow is at the starting index only. Let's say if we are trying to find the 10, let's suppose the target was not 3 but the target was 10. So in that case we can just simply return if we find our answer in the first binary search loop itself. So if our matrix of mid 0 is equal target, we will return true. Basically in this question we have to return is the element even present or not. So if the target element is present in this matrix we will return true, otherwise we will return false. So if we found our target at starting only, the starting index only, we will return true. Else if when our matrix of mid of 0 is greater than target, our element is greater than target. So our element which we are trying to find, our element which we are trying to find is greater than, our element which we are trying to find is smaller than ARR of mid minus 1 na? So we are trying to find 3 here, so we need to search on the left side. In this case, if I am not wrong. Matrix of mid is here, middle calculation is greater than our target, so target will be at the left side, so we need to search on the left side. In order to search on the left side we reduce our end, because we need to shift our middle to the left, so we will shift our end to the left. So it will be end is equal to mid minus 1, else it will be start is equal to mid plus 1. This is the right case. If we want to search in the right part we will do this. Okay, so this is correct. Now as I have explained you, we needed that end index. I have told you this, we needed this end index to find the correct row which we are trying to look. Now after this first binary search iteration we will find our appropriate end, basically appropriate row to find our appropriate answer. So for this example, in this case our end will be 0. This E after this iteration will be 0 for this example. Now we have this row, we just need to binary search in this row. So now we will define a start 1 and a start 2 again. Now we will define start 2 and end 2, a different variable, because we have already used start and end for the row wise binary search. So let's just call it S2, it will be 0, and now it int E2 will be n minus 1. So now it E2 will be n minus 1, because now we are searching from here to here, so it will be 0 to n minus 1. Earlier it was m minus 1 because we were searching from here to here, 0 to m minus 1, but now we are searching from here to here, 0 to n minus 1. Again our while loop, while our S2 is less than equal to end 2, we will calculate our middle. Let's just copy this code only. In this code it is, we got our row is this row. So what was the way to get this row in 2D array? It is defining something like this, that our end index which we have already calculated, this was the previous end, so here the middle calculation will be something like this, and now this 0 will be middle, because now we are searching in this x-axis, and this matrix of E will return this array, the first row array. Let's just do here also that, and this is E2 and this will be S2. If we got our answer here, we will return true, but if our answer still does not came, finally we will return false, that at last we get that the answer is not present in the whole matrix. I hope this should run, this should work. Yup. So there is one error occurring, that is an out of bound error, basically a -1 is occurring. So it is quite simple, because let me try to explain this case why this is failing. So it is failing for something like this, when our matrix is simply a 1. Now in this case, and our target is 0, so in theory we should return false for this case, but what is happening is there is some issue occurring. So let me just quickly dry run this and try to explain you guys why this issue of -1 is occurring in this case only. So we were trying to find our end, so that to restrict our search space to a particular array, to a specific row. So in order to do that, what we were doing is, at start we were initializing s to 0, our end will also be 0 here, because it will be m minus 1, which will be 1 minus 1, so end will be again 0 here. By doing this, our middle calculation will be 0 again. I hope this is correct. So basically our start, end and middle all are pointing to this 1 only. Now let's just see if our target equal our ARR of mid of 0. Is this the case? No, because our target is 0 and ARR of mid of 0 is 1. So this is not the case. ARR of mid of this is 1. So this is not the case. Now let's just see another if condition, because this if condition will fail. So what is the other if condition? That if our target is less than ARR of mid 0. Our target is, as you know, is 0 and our ARR of mid of 0 is 1. So this condition will get satisfied, and for this if condition, what is the step we do? Basically it is saying that our target is 0 and you are at 1, so you need to search in left side, and in order to search in the left side, we update our end to middle -1, and in this case our end will become -1, and this is where this -1 is coming from, the error -1. This is why this is occurring here, because it is trying to find matrix of -1, that is giving an error. So do one base case check here, that if our end is less than 0, we will return false in that case, that no, that element should not be present in our array. Yep. So now it is accepting. See how a simple if condition was failing our more than 100 test cases. Now only last question for the binary search algorithm is left. So let's just quickly try to solve that also. So in this question, suppose an array of length n sorted in ascending order is rotated. Okay, so before solving this question, let me just tell you one more thing. Sorry. The previous question which we just solved, that was this question, I believe, search in a 2D matrix. So they were asking the time complexity must be order of log m cross n. So what is the time complexity of our algorithm which we wrote? So let me just try to tell you that this one is order of log n, because we are sorry, this first one is order of log m time complexity, because our end is m minus 1 and we are starting from 0, and you know, when our length is n and we are starting from 0, binary search is log of n time complexity. So this is log of m time complexity, and this is log of nth time complexity. So it should be something like log of nth time complexity plus log of m time complexity. This is for finding the row, this is for the finding the target element in the row, and this is finding the main row itself, our first binary search that we were using. So how this is coming out to be this time complexity that they were asking, because as you know, our solution get accepted, and it was beating almost 100% people also. So why our solution is this time complexity? This is just a simple math, because whenever there is log a plus log b, it is simply log of m cross n, and this is why this was order of log m cross n time complexity. This is why our algorithm was working in this case. So now let's just quickly try to solve our last question as we were doing that. So in this array, we need to return a minimum element that is occurring in a rotated sorted array. So we just solved the rotated question where we find the pivot index of that, and we do left search and right search. In that case, the array was rotated. If you remember that in this question where we search in rotated sorted array and define the pivot index, that was the rotated array question only. So what we can do is we can just directly copy that question and paste it here and do some workarounds and get the answer. But let's just try to write the code from scratch for this question also. Suppose an array of length n sorted in ascending order is rotated between 1 and n times. For example, this might become this we know. This is the properties of the rotated array. How to identify that? Given the sorted rotated array, nums of unique elements, so no repetition of any element is there in the array. Return the minimum element of this array. So we don't have to return index, we have to return the element itself. And you must write an algorithm that is order of log n, because if this was not there, it is very trivial. We can just run a for loop and find what is the minimum element in the array. As you know, finding a minimum element is order of log n time complexity in the best case scenario. But as this is the sorted rotated array, we will do this in logarithmic of n time. Okay, so let's just quickly try to copy this base, this case 3 4 5 1 2. 3 4 5 1 2. So it is clear, it is quite clear that it is rotated 2 times in the left side. I have already explained what the rotated array means in the previous question, so I don't think we need to like relearn those concepts here. In the previous question, what we were doing is we were finding this pivot index. We were finding this pivot index. We were finding this pivot index using our modified binary search algorithm, and we were doing a binary search here and here. If you remember correctly, we were doing classic binary search on this side and on the right side, because now if you only see the left side, it is sorted array, and if you only see the right side, it is also a sorted array, and we were just searching on both of the sides. If we find our target, we were returning that. But the main concept, this is even simpler than that question, because let's say we somehow get our pivot index, and the question is asking the minimum element. So it is quite clear that if we find our pivot index, the minimum element will be the next to it. Let's say our pivot index is 0 1 2, pivot index is 2, then we just have to return ARR of pivot index plus 1. It will be at the right of the pivot index, because of this rotated property that sorted rotated array will satisfy. You can think of this, why this will always occur, why our pivot index plus 1 will always result in the smallest possible element that is there in the array. Because you can think this like this. Let's say our array was this, in first rotation it will become something like this, and in the second rotation it will become something like this. And our pivot index definition was that it is greater than its left and it is also greater than its right, and the only element that will satisfy this property will be the greatest element present in the whole array, and to the right of that will be the smallest possible element that is in our array, because of this rotation that I did. You can take any example and it will satisfy that property. But only one base case is there where this property will fail. Let me show you that case also. Let's say this is our example. Here, as you can see, this is rotated 0th time, but it is still a valid rotation. But here our pivot index calculation will give our pivot index to be this, but here there is no pivot index plus 1 to give our answer, because we were returning pivot index plus 1. We were returning pivot index plus 1. But here if we try to return pivot index plus 1, ARR of pivot index plus 1, it will give out of bound error, because it will try to find that element which is not present in the array itself. So in this case only, that there will be one extra condition, that if p underscore I is somehow greater than our end or n minus 1, we will return ARR of 0 itself, because somehow, let's say if there is no rotation occurring, this is the case, but let's say if there is one rotation occurred, so then this one will only go to the right of this. So if there is no rotation, we just simply return the first element, that will be the smallest element for that array. So I hope this is now clear, and to be fair, pivot index code I have already written in and explained that in the previous question where we were finding this pivot index here. Let me just quickly show you that in this question we were calculating this pivot index. So if I just copy this here, the pivot index calculation, and do that check which I just showed you, that if pivot index plus 1 is greater than our length, we will return ARR of 0, otherwise we will return ARR of pivot index plus 1. Then this should work. So let's just try to do that only. Why to write a code from scratch? Yeah, let me just explain this here only. Okay, let's just quickly copy this and try to explain that there. As our previous question array was nums, so let's just quickly change the name of this to nums. Now after this while loop, our pivot index should be initialized, and as I have discussed with you, that if our pivot index plus 1 is greater than our end, then we will return nums of 0, otherwise we will return nums of pivot underscore I plus 1, the next element to the pivot index, because the pivot index is the greatest element and we need to return the minimum element, which will be the right side of this pivot index, that will be pivot index plus 1. And this if condition is we are writing this because let's say if p underscore I plus 1 somehow somehow goes out of the bound, in that case we are countering this thing by writing this if condition here. Okay, so our base case is only failing because see here the rotation is at 0 times, because this is already sorted. 11, 13, 15, 17 is already sorted. There is no rotation. That means there is 0th rotation or there is nth rotation. The size, let's say the size of the nums is 4. So there are 4 rotation occurred. If the 4 rotation occurs, that means there is no rotation occur. Basically it is something like a circle concept. 0 degree same as 360 degree. So either the rotation is 0 or the rotation is equal to the size of the array. So this is failing. I know this is failing because we need to do this, I guess. Or more like this. Pivot index plus 1 should be less than our n. This was quite easy. In that case we will return this, otherwise we will return nums of 0. Okay, why this is failing again and again? We can do some trickery here and trick the system here, because what is happening, I believe, let me just see this. Okay, so what is happening is that our pivot index plus 1 is satisfying even for this condition also. So what we can do is we can return math dot min of nums of p underscore I plus 1 comma nums of 0. In that case we don't even need, okay, we need this condition. Yes, so now it get accepted. So what I did, it is not a trick basically. Let me just try to explain you guys why our code was failing, and what I did there was, mm, so in this case our expected outcome is 11 because we were expecting that our pivot underscore index plus 1 will be at here and it will return 17 as its answer. And when we will do pivot index plus 1, our out of bound case will occur and we will just return nums of 0, this 11, and we will be good to go. This is what we were doing. But what is happening in the question is, when when this array is sorted, when this array is sorted like this, when this array is sorted, we were expecting that our pivot index is at 17, which is at the the third index, but it was somehow at the 13th. It was pointing at the 1th place. Some issues were occurring. We can't even call that a issue because this is a special case in the pivot index calculation. As you can see that with only one statement, that mat.min, it gets tackled and all the test cases pass, so we can't even call that a issue in our algorithm. This was the how the question was designed and how they were expecting a workaround in order to tackle already sorted array.